Hi, and welcome to the third lesson on um, connected particles, modeling forces for those objects. And we're going to be looking at equilibrium. You've already seen equilibrium in the past. Um, the key difference here is when we look at equilibrium problems where two objects are in contact with one another, we have to include um, the normal reaction force. But it's basically exactly the same. So if we remember that equilibrium means that the resultant force is equal to zero. So if you add up all the forces on that object, they should add up to zero. Because of Newton's second law, um, because the mass is not going to be zero, then if this is zero, if the force is zero, then the acceleration must be zero. Note, though, that that doesn't mean that the object is necessarily stationary. Often it will be, but just because it has zero acceleration doesn't mean it has zero velocity. It could be moving with a constant velocity. An object flying through deep space, far away from any gravitational poles, might be an approximation to that. We're going to look at cases where we've got objects sitting on a table. Maybe we're going to look at a magnet being held up against a wall. And in each of those cases, we need to consider the weight of the object, maybe the friction as it slides up against something, which I'm going to be generally labeling as Fr rather than F, because I want to treat F as solely the sum of all forces in Newton's second law. Here we're in contact with something, so this is going to have a reaction, sorry, normal reaction force. Maybe in this case, we're going to be looking at the magnetic pole of a magnet onto a frigidor. Okay, maybe we'll call that M. So we have to look at all of these different forces. At the moment, we're just going to be looking at forces that are all sort of perpendicular to each other. But later on, we will need to be able to model forces at an angle. We'll look at objects on an inclined plane, in which case weight won't be acting in that direction, it will be acting down, and all sorts of other things happen. We have to start including angles, but we're not going there just yet. I'm going to be using Newton's second law all of the time, but actually some people might correct me and say, well, it's actually Newton's first law, which states any object remains in equilibrium unless a force is acted on it. But I'm just going to be basically taking that as a special case of Newton's second law, because if the force is zero, then the acceleration is zero, and therefore it will just remain moving in a constant constant velocity, or remain stationary. Okay, all we've got to do today is have a look at two little examples, and then I'll let you have a go yourself. So here's this example about the magnet. We have a fridge door and a magnet. There we go. Okay, it's a 200-gram magnet. We have to, when we're using Newton's second law, use kilograms as the standard unit. So whenever you see grams, always convert that to kilograms. Okay, 0.2 kilograms in this case. And we're just going through that first step of converting the paragraph, the words, into some sort of diagram to help us understand it. That's always your first step. So magnet, fridge door, okay, 2 kilograms. It rests in equilibrium. Okay, so I know my sum of my forces is going to be equal to zero, or equivalently acceleration equals to zero. Just a little note, something like that might help you. The magnet pulls towards the metal door with a 5 Newton force. So we're going to have something like a 5 Newton force. The normal reaction, we're being asked to find the normal reaction force and the frictional force. Okay, so the normal reaction is perpendicular to the surface, and the frictional force, well, we're expecting gravity to be acting downwards, so that'll be our weight, and we therefore have friction acting in the opposite direction. We've not spoken about friction much, but friction always opposes motion. So if there is a force that looks like it's going to cause the object to move, then friction will act in the opposite direction. I've always said to draw your diagram and then draw separate diagrams for each object involved. We've kind of done that already. We could do one for the magnet and one for the fridge door, but since I'm not interested in the fridge door, we're just interested in the magnet, we can kind of ignore this one. And I'm just going to relabel this. So we're going to have friction acting out, we don't know what it is. The weight we know is 0.2 times the acceleration due to gravity. The magnetic force of 5 newtons acts this way, and we know that the reaction force is going to be moving that way. It's going to be pulling in that direction. These are all measured in newtons. Maybe you don't need to write that on. So hopefully, thinking about the fact that the forces must all add up to 0 makes it very obvious what these forces should all be. We should be able to write down straight away that the friction must be equal and opposite to the weight down here. So that must be equal to 0.2 times g. If we take g to be equal to 10 meters per second squared, just for simplicity, that means we're going to end up with 2 newtons. And again, the same for the reaction force. We can see that's just going to be equal to 5 newtons because it's equal but opposite to the magnetic force pulling it towards the fridge. However, sometimes, like in the next question, we won't be able to just sort of see the answer necessarily. So it's helpful to kind of have a process. But what if you come across a question that's really tricky, it's got all sorts of strange angles and everything in it? And so I'm going to go through what looks like a long-winded solution, but hopefully it'll be more helpful in the future. So first of all, I'm going to simply apply F equals ma vertically. And I label that because if someone's going to be reading my solution, they're going to want to know where the next equation comes from. So I'm labeling vertically. I'm only interested in these forces. I'm taking up as my positive direction. Oops. And so we're going to have friction as being positive, minus 0.2g being negative because it's going downwards, equals mass times acceleration. Well, acceleration is 0, so mass times 0 is 0. And then we get straight to that. And so the only difference on a more complicated question is you might just have more forces being involved in here, maybe with some sine and cosine angles in there as well. Again, we then do the same, F equals ma horizontally. And we're going to get, let's take that as our positive direction. So we're going to get 5 minus r equals 0 as a substitution in, and again rearranges to that. So it's pretty obvious, hopefully pretty straightforward. So for the next question, this one here, have a go at it and then pause the video and then play the video again, and here's my solution. So let's start by drawing a diagram. We've got a 2 kilogram magnet again, resting on a horizontal metal table, clearly. So I'm going to label that as 2 kilograms. And so we know immediately we're going to have some weight acting down of 2g. It says that the magnet pulls towards the table with a force of 30 newtons. So we've got an extra 30 newtons pulling us down towards the table. And a child is trying to push the magnet along the table with a force of 50 newtons. But it remains in equilibrium. Well, that means there must be friction or some other force acting to hold it still, opposite in direction. So if the magnet is likely to slide that way, then friction must be acting in the opposite direction. And we're being asked to find the normal reaction force. So we need to make sure we've included that, because again, if it was just these two forces acting on this object, it would start moving down. So there must be a force pushing this object upwards to counter the two pushing it downwards. Again, this is now all the information that we need. I would often recommend drawing separate diagrams for each object, but we've only got one object here that we're interested in. The table is basically being ignored. So let's apply F equals MA. We'll go vertically because we want to find a normal reaction. And again, this is a bit long-winded. You might be able to jump straight to the answer. Make sure you understand what I'm doing here, because as the questions get harder, you're going to want to be able to use this method. So we'll take upwards and leftwards to be our positive directions. And so we're going to have the reaction minus 30 newtons minus 2g is equal to mass times acceleration, which is 0. So we're going to get R equals 30 plus 2g newtons. If, again, g is equal to 10, just because it's easier, we can say then R is 50 newtons. Find the magnitude and direction of the friction between the magnet and the table. So in this case, we're going to want F equals MA horizontally. And again, you can just write the answer down here, but I'm going to go a bit over the top and just write out this whole thing. There we go, we've got a substitution into our formula, and so we're going to get friction equals 50 newtons, but they want the direction. So here we just have to describe it in a way that's clear. There's no, necessarily positive direction described in the question. So we just need to say some way of describing this. We might say opposite to the direction the child is pushing in. And it's just some sort of description like that is all you need. So we have here our answers for part A. Okay. It then asks, what's the smallest force that the child would need to lift the magnet vertically off the table? So here we're basically trying to answer a completely different question. We're going to need a new diagram. So let's do that down here. B. This time the child is pulling this magnet off the table, pulling it upwards. Okay, I'm going to label that as P. Okay, for pull. Let's just get rid of that for now. What other forces are going on? Well, we've still got the 30 Newton force pulling it down. We've still got the weight of the object, which is 2 times g newtons. This time there's no pushing force in that direction, so there's no friction force trying to stop it from being moved. There's just this pulling force. Now, the other force we might need to include is the normal reaction. Let's just recap what the normal reaction means. It means that we're two objects are in contact, and as one pushes on one, there's this equal and opposite force in the other direction. But what's happening here is that this object is being lifted off the table. And so we want to know the force required by the child to completely remove those. And so we would expect the normal reaction at that point to be 0 newtons. They're no longer in contact, or it's at the point at which it's going to be just lifted off the table. So the normal reaction is 0. So apply again, F equals ma vertically, and we're going to have the pulling force minus 30 newtons minus 2g equals 0. Now here, why 0? Because it's the smallest force. We're basically at a position where we call this limiting equilibrium. Can't write it. Limiting equilibrium. And this is the point at which, if the force were increased any further, then it would start to move. It is the point at which this magnet is no longer resting on the table, but not being given enough force to start moving it off the table, not enough force to start accelerating it. And so we call this, as I said, limiting equilibrium, and that's when the acceleration is still equal to 0, but it's at the point of moving. The acceleration is at the point of just starting to become greater than 0. And so that's why here we've got 0 there. And so again, we can finish this off. P must be equal to 30 plus 2 times g, which if g is 10 is 50 newtons. And there is the answer to that question. I hope that makes sense. Have a look at exercise 19C. At least be doing questions 1 through 5, although I think 1 through 7 or even further you should be more than capable of. Have fun.